When complex software systems fail, the root cause usually isn't a single bad line of logic. It is unmanaged coupling. It's what happens when every object in a system has unrestricted permission to read and mutate the state of every other object, creating a tangled, fragile web. Encapsulation enforces stability by establishing strict topological rules for data movement. In this diagram, we see the toolkit Java uses to enforce these boundaries, 4 escalating access modifiers. Moving from the tightest restriction to the widest, we have private, default, protected, and public. To the compiler, these keywords are a simple vocabulary check. To the architect, they function as physical walls, spatial constraints that dictate exactly where data can flow. We are going to reconstruct a secure Java architecture from the ground up. We will start at the absolute center, the most isolated microboundary, and build outward layer by layer until we reach the fully exposed macroboundary. The following reconstruction treats code as a 3-dimensional facility, where every access point is locked down by default to ensure system integrity. The foundational atomic unit of object-oriented space in Java is the class. Every piece of state and behavior must live inside one. When we need to secure the internal state of that unit, we apply the strictest form of visibility available, the private modifier. Look at this structure. This single square represents a Java class containing a central piece of data. When we label that data as private, we construct a thick, impenetrable perimeter. The strict rule is that a private member is accessible exclusively within its own class. Internal methods living inside this specific class boundary can freely read and write to that central data node. But if an external class attempts to query or alter that data, the request hits the perimeter and is aggressively denied. This isolation is why making data private is the default best practice in Java. It guarantees that the state of an object remains predictable, shielded from the side effects of outside interference. The private modifier creates absolute systemic trust. It ensures a single class is the sole dictator of its own data. A single isolated class rarely builds a complete feature. Real applications require multiple classes collaborating closely without exposing their internal mechanics to the entire system. To group these collaborators together, Java uses the package boundary, effectively a spatial folder containing related classes. This brings us to the default access modifier. You apply this modifier simply by typing nothing at all. When you omit a visibility keyword entirely, Java assigns default access. Notice this larger bounding box. This represents the package, and it encloses 3 distinct class squares. The rule for default visibility is that access is strictly contained within this exact package. Because these sibling classes live inside the same package, they can freely interact with each other's default data, sharing information seamlessly. However, the security perimeter remains intact for outsiders. Any class residing in a different package hits the exterior wall and remains completely locked out. This architecture allows developers to build interconnected, multi-class subsystems while hiding all their internal wiring from the rest of the application. Default visibility effectively creates a secure, collaborative silo. In the industry, we often refer to this boundary as package private. Pure spatial grouping handles most scenarios, but a strict package boundary has a major limitation. Sometimes, 2 objects share a structural relationship but must live in completely different packages. This happens when we use cross-package inheritance, specifically establishing a parent and child class relationship across architectural divides. To solve this, Java provides the protected access modifier. This modifier has a dual nature rule set that frequently trips up junior engineers. Here we see 2 separate package boundaries, package A and package B. The first half of the rule is that protected acts exactly like default. Any class within the same package, like this neighboring class in package A, can successfully access the protected data inside the parent class. And as expected, a standard unrelated class over in package B is deflected at the boundary. The second, critical half of the rule is where protected differentiates itself. It grants a highly specific loophole. Access is allowed to a child class, even if that child resides in an entirely different package. We label a class in package B as a child class. Because it inherits from the parent, a targeted bridge forms, piercing straight through the standard package boundaries, based entirely on this hierarchical bloodline.
If this data were default, that cross-package bridge would be impossible. Protected access is the only tool that permits this specific external inheritance connection. Therefore, protected is a hybrid boundary. It blends local spatial grouping with remote hierarchical coupling. Now we expand our view to the final architectural perspective, the macro level of the entire software project workspace. The fourth modifier is public, and applying it represents the absolute removal of encapsulation boundaries. Looking at this macro view of the complete system, watch what happens to this specific public node. Its borders turn completely transparent. The source rule is absolute. Public grants open access across the entire project, regardless of class, package, or inheritance. Any node sitting in any remote corner of the system can draw a line straight to that public data and modify it instantly. The systemic danger here is immense. Exposing internal state globally reintroduces the exact tight coupling and chaotic access we identified as the primary cause of system failure at the beginning. The correct architectural use case for public is strict. We use it to define rigid API endpoints or global constants. We do not use it for everyday application state. Public should never be your default choice. It is a deliberate architectural sacrifice, trading local isolation for necessary system-wide communication. This topological approach transforms a series of syntax rules into the intentional construction of a secure software facility. We can visualize this entire facility with this concentric diagram, showing exactly how the four constraints nest within each other. Layer 1 is private, which strictly isolates data to the central class core. Layer 2 is default, expanding that perimeter out to the local package ring. Layer 3 is the exception, protected, which bridges the package ring exclusively for the hierarchy wedge. And the macro level is public, which completely exposes the element to the entire project perimeter. By mastering these four boundaries, engineers stop writing mere lines of code. They begin architecting robust, securely encapsulated systems.